Good morning, ladies and gentlemen. This is our first lesson in the new unit about rational functions. So we're going to start with graphing rational functions. So let's back up a little bit and just kind of learn how rational functions are different than the other functions we've dealt with. So if we look at these two, this set of slides, you'll see that this is a pattern that you know of for linear functions. So these all graph as lines. The ones in the middle, those are quadratic functions because they all have an x squared term in them, and those all graph as parabolas. And rational functions are the last ones. So rational functions, you'll notice, look quite a bit different. Rational functions are always fractions, so there's always a numerator and a denominator. And rational functions can include many powers of x. So this is x to the 0, or 1. This is x to the first. Here's another x to the first. There's an x squared. We could have x cubed, x to the fourth, all kinds of things in rational functions. But rational functions are fractions that can have polynomial expressions either in the numerator or the denominator. These are graphs of those same kinds of functions. Linear functions we're really familiar with. You know, they graph lines, you know that. Quadratic functions in the middle graph those pretty parabolas. And rational functions do all kinds of things that are unexpected. So we don't always know what to expect whenever we're graphing a rational function, but we're going to learn a little bit today about what some of the things, some of the ways we can make some predictions and some of the things that tell us important information about graphing rational functions. So, sorry, I'm having all kinds of weird things pop up. So, if you're in class, you're going to grab a graphing calculator, and when you do that, you will get these two graphs. We're going to be using a graphing calculator quite a bit because that's going to be good practice for you. You need to know how to use that graphing calculator really well. So if we graph the equation that's shown on the left, we get a line, and if we graph the one shown on the right, we get a parabola, and you can tell that because of the format of the equations. So that's a little background about how to kind of situate what these new rational functions look like. So if we graphed this function 2 over x minus 5, we would get this result. And notice I've got two lines on there in red that are dashed lines. We're going to talk about those in a minute. Those are really important lines. Our graph will get as close as possible to those two lines, but it will never touch them. All right, so the next function is shown here in blue. Again, I have the two red lines that are shown with our graph getting as close as it possibly can to those two red lines, but without crossing it. But notice right here in the middle at x equals 1, there's no value for the function that equals x equals 1. Then the last one, same sort of idea. This one only has one of these kind of forbidden lines, the x equals negative 2, where the graph gets close to x equals negative 2, but it never touches it. Let's talk a little bit about what those things mean. So the situations we just saw where we had lines that our graph got close to but wouldn't touch, those are called asymptotes. So we have both a vertical asymptote and a horizontal asymptote. So a vertical asymptote goes side to side on the graph, and a horizontal asymptote, a vertical asymptote goes up and down, and a horizontal asymptote goes side to side. So here are some examples of rational functions that are graphed. And here in the one in the center, you can see two asymptotes that are shown with the dashed lines. And in the one on the right, you can see one vertical asymptote that is shown in the pink dashed line. So let's kind of see how we would do that. All right, so a vertical asymptote is always in the format of x equals some number. So in this case, x equals 5. So remember, too, that vertical means up and down. So it's always going to be x equals all the values for x on the graph. And the graphed lines will get as close as possible to that asymptote, but never touch that asymptote. That's the definition of an asymptote. So that's super, super important. Now, why would that happen? Why does it turn out that way? Well, if we look at these examples of functions where where 0 is in the denominator, then you can see that when we divide all of these by 0, then we're going to get a number that's undefined. So when we have a function that has a 0 value in the denominator, then the function can never be valid for that particular value of x. So if the denominator is 0, then there's no value for f of x, and there's a kind of a hole in the graph. So as it says in the box on the bottom, the hole in the graph is described by the asymptote. That's kind of what the asymptote identifies for us. And in math terms, it means that the domain of the function excludes the x value that causes the denominator to be 0 at the particular value of that asymptote. So how do we find asymptotes? It's not particularly hard. We said earlier that the big problem with these fractional sort of rational functions is that the denominator can never be 0. So it says there in that little starred box, you can't divide by 0. So we have to figure out what value of x makes that denominator 0, and then we exclude that, and that becomes our vertical asymptote. All right, so let's try one. So here, x minus 5, well, x minus 5, if we set that equal to 0 and we solve for x, we get x equals 5. So we know that we have a vertical asymptote for the function on the left that's x equals 5. Then the function on the right is a little bit more complicated. If we set that denominator equal to 0, we have to factor x squared plus 2x minus 8. So x squared plus 2x minus 8 can be factored in the two binomials, x minus 2 and x plus 4. And then because of the multiplicative property of 0, x minus 2 and x plus 4 each have to, one or the other of them has to be equal to 0. So that's what the line is. It's second from the bottom. It shows where we're setting each of those factors equal to 0 and then solving. So the value x equals 2 and the value x equals negative 4 causes the function on the right to have a denominator that's 0. So we will have two asymptotes for the function on the right. Two vertical asymptotes, one at x equals 2 and one at x equals negative 4. All right, well, let's look and see how that looks. So here was the vertical asymptote we just solved for, and this is what the graph looks like. So the graph gets close to x equals 5, but it will never touch it. We're going to talk about horizontal asymptotes later, but vertical asymptotes are just the up and down behaviors for this at this point. So now this one looks quite strange. So when we graph this one, we're going to have two asymptotes. So we have two dashed lines that we're going to put on our graph. And our function graphs like this, where we have three pieces to it. So this one is really quite strange. So remember, what I said before about the asymptote kind of creates a hole in the graph. The one on the left, we have one vertical asymptote, so it made one hole. The graph on the right, we have two vertical asymptotes, and there's two holes in the graph. So vertical asymptotes are x equals a certain value. Okay, in class, you're going to practice this. So that's what this is for. If you have the practice page in front of you, then I suggest you go ahead and find the vertical asymptotes for each of the functions on that practice page and draw a colored line like these pink dashed ones you see on this page, because that's kind of a starting point for every graph. So I thought we'd go ahead and practice just vertical asymptotes first. All right, next we're going to talk about horizontal asymptotes. So those are the side-to-side lines that the graph will get close to but never touch. And there's two cases for those. There's a situation where we're going to pay attention to the degree of the expressions in the numerator and the denominator. And if you remember, the degree of a fraction, or the degree of an expression, is the largest exponent. So an x squared value has a degree of 2. An x to the 7th value has a degree of 7. An x to the first value, or just a plain old x, has a degree of 1 because it's x to the 1. So if we look at this case 1 that's listed over here, we have our first one is y equals x over x squared. And you could consider that one that is bottom heavy because the numerator of the bottom has a higher degree the exponent of the bottom, or the denominator, has a higher degree than the exponent of the numerator. So that one's bottom heavy. So that one is an example where we have a horizontal asymptote at y equals 0. Another one example on this page shows us we have y equals 3 over x. Well, so the denominator has an exponent of 1. The top has no x at all, so that one is definitely bottom heavy. There's more x's on the bottom than on the top. So that's a good way to think about it, that if there's a higher number of x's as far as the exponent goes on the bottom than on the top, then that's considered bottom heavy and y equals 0. So here a couple more examples of bottom heavy ones that are a little bit more complicated. Now case 2, so it's shown here in yellow that our asymptote is y equals 0 for this case. Sorry that this video is not quite as smooth as some of them I've done. I'm doing this early in the morning before school and I'm trying to rush through it, so sorry about that. So the next case, so we have one case where horizontal asymptotes we know that y equals 0, the horizontal asymptote y is 0 whenever the exponent of the numerator is smaller than the largest exponent of the denominator. It's a lot of words. It's not as complicated as it sounds. Then the second case is when the degree of the numerator and the denominator are the same. And when that's the case, we take the leading coefficients of each of those values and create a fraction. So in this case, the top one, we have an x to the first in the numerator and an x to the first in the denominator. So we look at the coefficients on the x. The coefficient on the numerator of the x is 3. The coefficient on the denominator of the x is 1. So the asymptote for the top one is going to be y is equal to 3 over 1, or 3. The one on the bottom is a little bit more complicated. We're going to look only at the matching coefficient. So we're not going to use that value of 3x at all. We're going to ignore it. We only want the ones with matching exponents. So we have an x to the 4th term in the numerator, and we have an x to the 4th term in the denominator. So we're going to take those two. They do match since they're both x to the 4th, and we're going to take the coefficients of each of them and put them in a fraction, and that's going to be our horizontal asymptote. So the horizontal asymptote for the one on the bottom is going to be y equals 5 over 2, because 5 was the coefficient on x to the 4th in the numerator, and 2 is the coefficient of x to the 4th in the denominator. Okay. So if you were in class, I'd ask you to just do all of the horizontal asymptotes for the practice page. So if you have that at home, you should be doing that as well. And you're going to draw a line just like we did before at those horizontal asymptotes. Horizontal asymptotes are always a y equals value, and there's always only one horizontal asymptote. There can be multiple vertical asymptotes, but there can be either one or no horizontal asymptotes. You'll never have more than one. You'll have 0 or 1 horizontal asymptote. Okay, so here's some of the problems that you need to do. These aren't completed. There's some examples online, but hopefully this video will help you kind of get started. Remember to use these cases for the horizontal asymptotes, and for the vertical asymptote, follow the button that's listed there by setting the denominator equal to 0 and solving, and that's the value that makes the function undefined. So the vertical asymptote is going to be on this one. It's pretty easy to see. The vertical asymptote for the function provided is going to be x is equal to 2. And on the example that we're given, let's look at the two cases for the horizontal asymptote. In case 2, we have to have an x value that has a matching exponent. Well, we don't. We have an x to the first in the denominator, but that's all we have. We don't have an x to the first in the numerator. So that means that our horizontal asymptote is y equals 0. And you know how to solve for a y-intercept. The y-intercept is the value for y where x is 0. So if you solve for that, that's kind of helpful for graphing these, but you can get out your graphing calculator and determine how it actually looks once you know what the vertical and horizontal asymptotes are. Alrighty, thank you for watching this video. Good luck, and keep in mind that these look kind of strange, but they're really not that difficult, particularly when we use our graphing calculators or Desmodes. If you need to use Desmodes, you can do that as well. So I'll make sure that there's a link to Desmos on Canvas if you're at home and don't have a graphing calculator that you can use. All right, thank you.